In this video, we're going to be looking at Mott Insulators. But before we look specifically at Mott Insulators, we're just going to go over a quick recap of insulators and conductors in terms of band theory. So this is an insulator, or this is usually an insulator, I should say. We have the energy axis up here, and then some k-axis along here. So this is like a dispersion relation. I've highlighted in this pinkish reddish color the states where it is occupied by an electron, and I haven't highlighted it when it's not. In this case here, if we apply an electric field, an infinitesimal electric field, there's no where for these electrons to move to. There's no free states which they can move to without having to jump a gap, which may be direct or indirect. So this is what we mean by an insulator, that an infinitesimal electric field doesn't cause a current, or doesn't basically change the state. A conductor, we have a different situation. So here we have a conductor, and we have, in this case, overlapping bands. This means that if we apply a small electric field, some of these states near where the cursor is can move up a bit, or they can move, or some of these can move up, some of these can move up, or some of these move up. We can basically create a current by moving these electrons between states. And that's what we mean by a conductor, something that when we apply a small infinitesimal current, a small infinitesimal electric field, causes current to flow. We can also have a situation like this, which is analogous. We have here a one full band and then this half filled band, which again you can have a small infinitesimal changes of states when electrons move. So looking at this then, you would think this would be a conductor, because you can have these changes of states as these electrons move. But that might not always be the case. When you have structures that I've been showing you, ones like these, they usually are conductors, but they might not be. And this is where Mott Insulators come in. And to do that, we're going to look at a small example using three atoms. Atom A, atom B, and atom C. And these three electrons. Now we're going to be assuming a tight binding model. So we're going to assume that the electrons basically stay on atoms. And in a normal case, if we apply an electric field, the electrons will move. They'll move to decrease the energy. So you'll get a situation that looks something like this, where you have more electrons over here and less over here. But in a Mott insulator, there's an energy payment, I guess, for being in such a state like this. This is to do with electron and electron repulsion. These two electrons repel each other, and when they're pushed close together, that means there's an increase in energy. So they don't like to be pushed close to one another. That means in a Mott insulator, you don't get a situation like this. You get a situation like this, which is identical to our initial situation. In other words, we don't get this current flow because we have these electrons backing up on each other. This electron can't go here because if it goes there, there's a massive energy. It needs a massive amount of energy just because the electron-electron repulsion between this electron and this electron. So that is the Mott insulator. That's the fundamental basis behind it. You have this electron repulsion, like a Coulomb energy, which prevents the electrons from moving, or this hopping as it's called. So you have like a balance between the electrostatic repulsion and the kinetic energy, the movement or the hopping of these electrons between states. That's what we mean by a Mott insulator. Thank you for watching.